let's go ahead and begin with coordinate systems. What does that mean? So a coordinate would be either 2 or 3 numbers, okay? And they're going to specify a specific location somewhere on the Earth, okay? And now the thing is, they can be either reference to, let's just call it general world coordinates around the entire globe. So basically everything has the same reference, or they could have some other type of local reference to them. And in that case, that's why we say some origin. An origin would be like a known place, and then everything else is referenced to it. So if I know that my origin is here at 0, 0, then say this over here is 1 and 1, and then this over here would be 1 and 2. This over here would be 3 and 2, something like that. That's what we're trying to get across. So in the slide, like down here at the bottom, this would be 0, 0. And then in this case, we have an x-axis going this way to the east, and then a y-axis going to the north. Now, technically, we can go in any 4 directions, west and south. It's just that these would be negative numbers to the west, and these would be negative numbers to the south. What I'm trying to get at here, if this is 0, 0, then this point right here would be a 1 and an 8. So the 1, say, as an x, counting down from 1, 2, 3, 4, 5, and then moving along, something along those lines. Everything being very consistent in the spacing between those numbers. And then maybe 1, 2, 3, 4, 5, 6, 7, 8 here. Meaning that this coordinate in this particular location for that particular point is going to have an x and a y of 1 and 8. For all intents and purposes, we always put the x first. Not every single time, but in a lot of circumstances, that's really the way that things are supposed to be kind of written out in a sense. When we see a 1 and an 8, that means x and then y is what we're trying to say, the coordinate for x and y. And again, if this is 0, 0, we're, let's just saying it's some kind of local reference. In this case, maybe it's a house. This is some kind of, maybe this is actually the lot of a single family home. And so we've got a little small reference to work with. And in this particular part of the lot, this would be 0, 0. And then here are the different coordinates so that the person mapping this out can know exactly where those extents or those, endpoints should be. Basically connect the dots, and that's, let's just say, the footprint of this particular lot. Okay, great. So let's move on. Now, coordinates can be, let me shrink this down a little bit so you can see the whole title. Coordinates can be in either a 2D or a 3D, what's known as Cartesian planes. That's what we're looking at here, and it's what we just talked about a moment ago. The 2-dimensional would be something like this, which looks like just what we talked about. Having an origin always is going to be, technically this looks like it's at the bottom left, but this would be the middle of the space. Because like I said, we could go also in this direction to the west or in this direction to the south. 2 dimensions, we would be not having any elevation value. However, we can also throw in a 3rd dimension because, like I said, coordinates could have 3 digits to them or 3 integers to them. And so the 3rd dimension would actually have an elevation involved as well, which we would call, instead of x and y, the 3rd dimension would be the z value. Moving on. Now, there's something known as spherical coordinates, and essentially spherical coordinates are angles, because the Earth is spherical in the shape of its nature, and it's not technically flat. It's more or less kind of like a ball in a general sense. So to measure from one place to another, we have to kind of create little arcs as we're going from one location to the next. and so we call that a spherical coordinate. Spherical coordinates are defined as what's known as latitude and longitude, which we'll describe here in a moment. The origin of a spherical coordinate in this example is going to be 0, 0, which is going to be where the, equator and so the equator going latitude-wise, 0 degrees, and then the prime meridian, which is actually going to go through England here, as also 0 degrees longitude, okay? Longitude, latitude, let's just get into it and I'll kind of explain this a little bit better. So longitude and latitude first, also known as parallels. The reason we call them parallels is because they never actually cross each other. They just kind of go in the same direction, okay? They don't actually meet each other at all at any point. So the equator is 0 degrees latitude, and this is perpendicular to the spin of the axis of the Earth. But anyways, so the circumference of the parallels, it varies. The equator being the largest circumference. So the longest line, if we were to stretch that out, where the Earth is, let's say, the fattest. And then as we work our way up and down, either in the northern hemisphere or the southern hemisphere, like this, if this is 0, this would be the northern hemisphere, this would be the southern hemisphere. We would go, just like we had with the y-axis going up, all positive numbers defining latitude. And in this case, the very, very top at the North Pole is 90 degrees. And then the very bottom would be negative 90 degrees at the South Pole. Everything in between is going to be some number between 0 and 90 degrees, okay? So latitude actually defines your north or south, let's call it, location, and it splits the northern hemisphere and the southern hemisphere together, okay? Moving on. So next we have longitude, and longitude are also called meridians. Meridians because they actually cross each other and converge at the poles. Looks something like this when we get to, let's say, the North Pole. We've actually rotated the Earth a little bit this way. And they meet at the poles. Let's see. So the prime meridian, like we said, is 0 degrees longitude, which would be right here, okay? And this little island there, it's not really a great graphic, but that's the island of the UK. And in England is where actually the 0 degrees longitude idea came up, in a place called Greenwich. And Greenwich is the home of essentially where the beginning of the Western hemisphere, which would be west of England, and the Eastern hemisphere, east of England, that's where everything kind of starts and ends. On the other side is 180 degrees. So longitude is a little bit different than latitude in that sense. Longitude will go from 0 to 180, and then once you hit 180, it starts over again, or it goes backwards. So in that case, once we hit, if we were going from England eastwards or along Asia like this, and 180 is actually, and that's called the international date line, by the way. 180 is right along the Pacific Ocean. And so if we crossed 180 going this direction like this, kind of counterclockwise, what's going to happen is instead of these numbers increasing to 190, 200, et cetera, like that, they become negative because just like we looked at the XY plane like that, okay, now your longitude is your X equivalent. And so the Western portion, the Western hemisphere, are all going to be negative numbers. So things start going kind of backwards in that sense. In this case, we would go 150, 120, 90, and these numbers are arbitrary to the graphic. But we would go from 180 kind of in reverse order back to 0. And on the Western hemisphere, these would be negative values, okay? Let's see. The other thing about longitude is that they're all equal circumference, okay? Difference than parallels. Every single line of longitude is the exact same. And that's how they end up actually meeting in the middle. Well, I shouldn't say the middle, meeting at the poles. That makes more sense. Okay, a datum is an important term, and it's commonly used in GIS and geospatial science. So make sure you pay attention to this part. When we mentioned earlier a reference or an origin, okay, datum is a fancier word of saying that thing. Okay, so a datum would be the reference system of an approximation of the Earth's surface, and that's what the Earth is referenced against, with which positional measurements are referenced against to come up with locations. Let me clear that up. Basically, that whole idea of 0, 0, that would be where the datum is, okay, or that would technically be the datum. And that 0, 0 could be in completely various places throughout the Earth, okay, and we'll learn how what this means a little bit more in a second. If we're talking about just the spherical types of measurements, which was slide 5, then the datum is going to be in the middle, smack dab, like if we dug a hole through and created a radius all the way through the Earth, that would be where our datum exists. But if we were looking for elevation values as well. If all we're looking for is horizontal values, then our datum would be at 0, 0, which is actually right off the coast of Africa. Equator prime meridian. Nevertheless, the datum could be in multiple places, like I mentioned, and I'll explain that. So this idea of a datum, it's like thinking about how the Earth, as we know it as a sphere, how it makes more sense to redisplay that shape, because not all locations are going to be represented well in that case. Something known as distortion, which I'll explain here in a minute. So I'll try not to get too ahead of myself. Horizontal datums, these are used, that's like what I just mentioned here. So the horizontal datum for, let's say, latitude and longitude, the horizontal datum described a point on the Earth's surface, latitude and longitude, or another coordinate system. So a horizontal datum, if we were talking about spherical, the horizontal datum would be that 0, 0 location, okay? And vertical datum, these are just some common horizontal datums just to throw out there for you guys. If you see WGS 84, that would be known as the world geodetic system, which is spherical coordinates. And then North American datum 83 is going to be known as what's called projected, which is more XY kind of designations. But like I said, I'll explain this stuff. Vertical datum would be used to actually measure elevations. So vertical datum and horizontal datum, they technically are a little bit different. The vertical datum would be, like I said, if we drilled through the Earth and went to the center portion of the Earth, okay, that would be, and again, looking at spherical locations, that would be where our vertical datum is. Vertical datum is going to define the Z or the elevation, and then the horizontal is going to define the lat long or the XY. So yeah, about this whole idea of geographic coordinate system or GCS, and this is spherical or spheroidal, fancy word, right? So either truly spherical or what's known as something called elliptical, okay? Which I'll get to here in a minute. And it's going to approximate, it's going to be an approximation of the surface of the Earth, okay, an approximation. And we're kind of repeating ourselves here about our datum defining the surface, okay? It's what everything is referenced to, the datum. And let's see, the position of the surface is relative to the center of the Earth, just like I was mentioning here. So the center of the Earth being right there. Imagine this is a radius, and then where does that little radius kind of end up being pointed at? That would be the latitude and longitude in reference to datum. So yeah, all coordinates are referenced to some type of datum. Now, we said spherical or ellipsoidal. Ellipsoid, we got to get that big word out of the way because that's an important one to understand. So an ellipsoid, and I try to make this, I try to break this down in kind of as simplest way possible. When we talk about the actual shape of the Earth, yes, we get it out of the way. The shape, okay, when I say shape, I'm meaning kind of in a general sense, like a general conversation. The shape is a sphere. But to be more specific about that, um, the actual model of the Earth is not a perfect sphere. Okay, it's not a perfect sphere, meaning that um, it's actually more of an ellipsoidal shape or an ellipsoid shape. And an ellipsoid is like a ball or a sphere that got kind of squished a little bit. And so, you know, with a ball, you would have, if we did two radiuses going in kind of at a 90-degree angle, one going in one direction, one going in another direction, they would be the exact same length. With an ellipsoid, what we end up having is one of these two things being shorter than the other, okay? And that's technically what's going on the Earth itself. The radius to the poles is shorter than so the radius to the poles here is shorter than the radius to the equator, okay? Not by much, really. It's like only by a few dozen miles, if you can actually wrap your head around that. But it does make a difference. And so in this case, we're talking about making measurements. Ultimately is what coordinates are used for, and having precise location information. So this kind of discrepancy, the shorter side, in this case we have B, okay, for the poles, we call that the semi-minor axis, and then A being the semi-major axis. Minor for shorter, major being longer, okay? And so this kind of where the poles are is considered to be more or less a little bit flatter of a space. You know, to get even fancier with words here, oblate ellipsoid. That's technically what the model of the Earth is, not the shape of the Earth. An approximation of its shape. Yeah, I mean, technically this should say model. If we were going to really model the Earth, it would be ellipsoid, okay? Great. So with all that in mind, there's even more to this. While an ellipsoid makes more scientific sense and is more precise than just saying everything is a perfect ball. The fact of the matter is there's gravity on the Earth, which the gravity on the Earth actually is what essentially makes it the shape of a circle in the first place, because everything gets sucked into the middle, okay? And so gravity on the Earth is not all the same everywhere. Wait a minute. So there are different strengths and gravity forces in various locations on the Earth. Meaning that what I'm saying is that the gravity, not saying that if you go somewhere, you know, different than California, you'll float in space or something. That's not what I mean. But there is a different amount of pull involved, a stronger or weaker amount of pull involved, okay? And so ultimately what that does is it changes what the Earth's surface, really how that would be modeled in its most accurate and most precise representation or truest representation. Yeah, so let's see. Effectively, we call this whole thing, this concept of what we're talking about, we call that the geoid, a geoid model. And so before I start reading these things, let me just look at this graphic and try to explain. The Earth is not as bumpy as this, right? In terms of like topography. It does have variations in terrains and topography, obviously, with mountains and, you know, crests and other things, dips and divots with ocean floors. But that's not what we're trying to show here. These variations in colors and little bumps are exaggerated views of how strong the gravitational field is. And basically demonstrating that it's an uneven mass of distribution. Remember, gravity is pulling everything into the center, what's known as its center of its mass, okay, the center of its mass. And so that pull is varied, like say, for example, it's weaker over here in, I guess that's the Indian Ocean compared to over here, which is kind of the north part of the Atlantic Ocean, right, by Europe and Greenland, etc. Okay. Um, and so why does this all matter? Okay, why does this all matter? Well, it's important to know this information because it's very critical to having measured very precise surface elevations. If we're just trying to find latitude and longitude, this stuff doesn't even matter. Okay, it really doesn't. But if we're trying to add that third element, the z and the elevation value, having a geoid in place makes a difference because it is going to change what the where we're defining the ground is in variation because of this gravity on the Earth. So, you know, here's the thing. I don't think I have a slide about this, honestly. I was going to say something else here. When it comes to elevation, think about it for a second before I tell you this. So, say, you know, you're driving and you hit, you know, a new place, driving up the mountains, it says elevation is 1,000 feet. 1,000 feet compared to what? Compared to what, right? So 1,000 feet compared to, and in a general sense and for all intents and purposes, we're saying compared to what's known as mean sea level. So in that case, what we're saying is if 1,000 is where, say, the mountain is, 0 would be, we're saying that that mountain is 1,000 feet higher in elevation than 0, which is technically the ocean, mean sea level. And so mean sea level is meant to be kind of an average, it's a statement of averaged out throughout the entire ocean. But because of this gravitational variation around the Earth, 0 in the, where we define 0 and where the ocean is completely different all over the Earth. And that's ultimately what we're trying to get at here. And so it's 0 that's changing all over the place. Not necessarily I'm saying that because of tides, you know, that's another factor that gets thrown into this. But let's just, you know, I'm throwing out an example for you guys. So 0 here in, let's say, California, off the Northern California coast, well, we would consider 0 where the ocean is. In the exact same time, right, if we just, you know, spun all the way across the Earth to, say, even the East Coast, like, say, Miami or something like that, 3,000 miles away, still in the Western Hemisphere, the reference of 0 from in the ocean where Miami is technically going to be a little bit different. So it might actually be -2 or +2 or, you know, +5. I don't actually know the concrete answer for you. What I'm trying to say ultimately is all of that comes down to this variation in gravitational force and the way that is modeled in something known as this here called the Earth's geoid. Okay, the Earth's geoid. Let me come back to this slide in a second. What we're trying to ultimately, you know, answer in this, when we want to define what an elevation is on the surface of the Earth. So how do we know that that 1,000 exists? We have to take into account both the ellipsoid and the geoid because I'm going to get kind of technical here. So defining that particular point in modern times is used through GPS technology. Now, GPS technology is great at finding X and Y locations or latitude and longitude locations. The problem is that it's not exactly, and so let me back up. The reason why it's good at finding latitude and longitude is because it goes and it references spherical coordinates to do that, which it then references to make sure it gets the spherical coordinates. It references the ellipsoid of the Earth, ellipsoid model of the Earth. Now, the problem is, though, is that as we just viewed, the surface of the Earth and what is technically 0 is not smooth everywhere, okay, because of this idea of gravitational pull. And so we have to take the ellipsoid, and then we have to also take the geoid, and we have to compare the two things. And then we subtract the two and come up with what's known as an orthometric height. And an orthometric height is where you're going to end up with that 1,000, because the orthometric height is going to take both things into account, and then that is going to give us the most accurate representation of what a precise elevation is, or where it's located, okay? So here's kind of the best illustration I could provide of that. Now they've got best ellipsoid A, best ellipsoid B. Let's imagine that we're just working with A. Forget about, or I'm sorry, we're just working with B, the dotted line. Forget about A for a second. We're working with B. Okay, so this dotted line versus the geoid, which is this kind of gray line. And so notice that there's variations where sometimes the geoid is higher, floating above the ellipsoid. And then in other parts, it's actually, let's say, below the ellipsoid, okay? So knowing what that variation, or knowing what the difference is between those two, and that's going to be completely different in various parts of the world, because the geoid is kind of this bumpy looking thing. Knowing the difference between those two is going to ultimately give you guys, and somebody that's finding out these elevation locations is going to give them the most precise answer. Okay. So to kind of sum this up, I would say, if a z value is desired, what's necessary to know is an ellipsoid of the ellipsoid being used, which most cases, for all intents and purposes, is going to be the same thing for the entire world. But geoid model does have a little bit of change and variation. If we're working in North America, you know, I imagine everybody viewing this video would, it's actually all the same. So at least knowing those two things are going to make it possible to actually pinpoint, like, for example, what that 1,000 elevation is, okay? Takes into account the variation of, like I said, you know, if this is 0 here in San Francisco, then this is actually -5 in Miami or something like that, okay? Confused yet? Please ask me questions, because this stuff gets pretty deep, and I'm happy to get into this a little bit more. There will be questions on the second exam related to this, so it is important that you guys have an understanding and an overview of what we're talking about. So backing up, I just want to call out some common terminology for you guys. Latitude and longitude, it's going to be defined using, as we just mentioned, the ellipsoid, okay? Often called the horizontal coordinates. So in common terminology in this space, longitude is referred to as something called the easting, or called an x value. And then your latitude is called your northing, or your y value, okay? Now elevation, we have to have a geoid thrown into that mix as well. And so your elevation is also often called a vertical coordinate, or a z value, okay? Just so you guys know that for reference. Okay, so let's see, let's skip that. Now, moving on from this idea of the Earth is, say an ellipsoid, to something different than that, and something as we want to represent even more precisely on a local level, what's known as projected coordinates. And when we take a spherical shaped thing, or an ellipsoidal shaped thing with curved surfaces, and we want to make it flat, okay, just like any map you've actually seen printed on a wall, there's something called distortion that occurs, because when you have something that's 3 dimensions and then you make it flat, if you kind of squish it out, not all parts are going to remain equal, the same as they should. And so there's something called a mathematical transformation that has to occur to convert the locations of the points on a curved surface to something that's more of a flat plane, okay? Also, this is going to require a new datum, okay? Because projected coordinate systems they're technically referenced from geographic coordinate systems, but now think about that for a second. The datum is not in the exact same place it used to be. Let's see. Yeah, I kind of said this already, right? But let me repeat that. What this all entails and why it's important to something that's very important to know theoretically is that all projected coordinate systems, taking that three-dimensional sphere, ball, ellipsoid, whatever form you want to look at it, when you flatten that out, you're going to end up causing distortion to the shape of say something, or this area and the size of something, or the distance or direction of something. Okay, so here's some examples. Okay, challenge of looking at the left side versus what happens to the right side. You may have thought to yourself, if you look at this graphic here, and that's what you've known the world to be, Greenland is not actually this size in comparison to North America. It's actually much, much smaller size-wise, right? So the shape of it looks the same, okay? But the size, because it's now distorted compared to this version, is much different. Same with Antarctica, all right? So yeah, maintaining accuracy in distance, direction, and area. So think about this for a second. We are all working in a mapping software, and that mapping software is on a flat screen. So in all reality, everything you guys have been doing and will continue to do has been in this kind of reprojected world where the Earth itself has looked or has appeared to be somewhat distorted in some form, shape, or fashion. Okay. Other examples. Okay. So yeah, you've seen maps like this, and they look really odd. Well, the reason that a person would make something like that is to try and eliminate the amount of distortion that's going to occur. So kind of slicing things up in their most precise way possible. Obviously, then things look a little bit odd, but they're much more accurate and precise in that case. Let's see. Yeah, we talked about this a moment ago, right? We go from this to something like this on a regular plane. And then there are other ways of projecting, not just kind of a straight, kind of flat plane in a sense. Those other ways, first and foremost, let's call it out what that big flat kind of square looks like. Imagine what we've done there in those maps. What's actually happening is take a piece of paper and kind of wrap it around that ball. And then what that's going to create is a cylinder shape. Okay, and so that cylinder shape, then when it gets folded back out, it creates this kind of flat square or rectangle. And so the cylinder is really good as far as a projection is concerned. By the way, each one of these are called different projections, okay, different types of projections. So the cylinder is going to be really easy to use. The latitude and longitudes match up at right angles, which is what they're supposed to do. The direction is pretty true, okay, north, south, east, west, but the distortion gets worse the further away you get from the equator, right? The higher the latitudes, the more distortion occurs, which is why Greenland, being right at the North Pole, same with Antarctica being at the South Pole, are grossly distorted, okay? Something called an azimuthal or planar would be if, say, the idea was to only map like the North Pole, for example. And so again, still taking a flat piece, but only being able to represent, 30 degrees down from the center. You're going to end up with something kind of like this, which is going to be really useful in the poles. But then your direction and your distances are going to be a little bit off, but the shapes are going to be still pretty accurate. And at the same time, though, you're not going to get the whole globe, right? Then there's also something known as a conical, or which basically looks like a cone. And if you're looking to show really small areas, kind of like an even more localized picture of something, the conical is a pretty good option because the distortion is reduced. The more and more we can kind of shrink this down to in terms of what is being mapped, the less distortion is going to occur. Um, something known as, here we're looking at the cylinder kind of flipped around. So these little blue lines here are known as secant lines, okay? And the secant lines are the only part of the cylinder, are the only part of the projection where there is no distortion. That's not very much, right? Now, the thing is with a cylinder, because you have the ball kind of protruding out of the cylinder, you're going to get distortion inside of those lines look a little bit smaller. So essentially anything where the equator is, things look, actually the shapes are going to be a little bit smaller than they're supposed to be. Projection, or we should say where the globe is on the outside part of those secant lines, you're going to get features that look much larger. And looks like we have a visitor. And we'll move on. One of the most commonly used, besides latitude and longitude, projection is called the Universal Transverse Mercator, or UTM. Okay, that cylinder map that we keep talking about, effectively that is a UTM type of map. And so with UTM, what ends up happening is, and UTM is actually broken into these various zones, okay? And each one is a little bit, well, each one has the same amount of distortion, but they're broken down so that the distortion is kind of reduced. In the sense that, like we saw earlier with this map here at the top, this is the closest thing to a UTM as we can get, okay, this one here. Now, why does this all matter? Well, with UTM, we have about a 6-degree spacing in between. So 6 degrees of longitude is how wide each one, which is actually not that much. But let's see, horizontal cylinder touches globe at 2 secant lines for each zone. You end up with, because we've got these broken down into these, pretty thin slices, we end up minimizing distortion quite a bit. And there's much more accurate measurements that can be derived from like something like a UTM. And it's commonly used in ArcMap and ArcGIS. So how it works is each zone, okay, because there's these various zones throughout the world. Okay, UTM is a world type of projection. Each one of those 6 longitude degree slices are called zones. And so each zone has what's called a central meridian, and it's located exactly in the middle of the zone. Okay, so like here's an example of a UTM zone 11 north. Okay, so between these two things would be 6 degrees of longitude. Obviously, because they're meridians, then they get a little bit wider at the what appears to be wider at the closer they get to the equator. But nevertheless, what we're trying to get at here is this line here in the middle would be the central meridian. Okay, so these darker lines would be the definition of where the zone is. And what's going to happen is, as opposed to the measurements of latitude, longitude being like these arc lines that don't exactly translate well to, saying make a measurement of, how far is one road from another. That would make more sense to have something like, miles, or even more broken down to feet, meters, to much smaller values. So with UTM, the coordinate values are actually defined and measured in meters. Okay, and that's how it becomes this kind of world, the most world translatable type of projection. anyways, so we have meters. And so what's important with that is we still have to have an origin, which is a 0, 0. And every single zone has its own origin, okay? The origin is going to be, if I got it down here, see this little X there. Again, your datum, okay? The datum for, in this case, UTM zone 11 north. The origin is going to be actually offset to the south and to the west of the central meridian. And that's important because with UTM, the idea is to never have negative coordinate values. There should never be a negative coordinate value. The only way to have that is to have the 0, 0 down at the very bottom corner, okay? And so the origin for north is going to be at the equator, and then the origin for the easting, which is a little bit more complicated, but the origin for the easting, okay, which is going to define the longitude, the east and the west, is set 500,000 meters west of the central meridian, okay? So 500,000 meters west of, I guess, 3 degrees from one of the sides. I probably confused you an immense amount now, but let's try to understand this a little bit better. So if our central meridian is here, then everything in between here is going to have some kind of positive value, okay? So central meridian at 117 degrees longitude, west longitude, zone is 6 degrees wide, and the easting for this particular UTM zone north is going to be 500,000. Okay, 500,000 is going to be the value that's actually put there. And so the zone boundaries we would have, again, because there's 6 degrees of latitude longitude between them, we have a west 120 and a west 114 between these two bold lines. Now, imagine that we put a coordinate right there in eastern Oregon, and we were trying to find out, based on this projection, what would be the coordinate value for that particular place. So the easting would be the first thing that a person has to find out. And the easting, okay, the easting is going to be, let's see, in this case, because we know that the central part is 500,000, and so, and we know that right here is 0. So technically what we could do is go however many meters it is from the center to that particular point. And we ended up with subtracting, let's see, we ended up with something like 397,800 meters in easting. So technically that means 397 meters away from this, and what, 103,000 meters away from the center. And then the north, we have almost 5 million meters north, because the equator is much further away than that central meridian. Thing with UTM is there's always going to be the easting values in the hundreds of thousands, and then the northing values, excuse me, in the millions. Okay, so either 6 digits or 7 digits. Come on now. Okay. So this is important because say you're working on a project and the scope of the project calls for the values to be something other than arc, latitude, and longitude, and they need measurements in the map to be something understandable to kind of a layman's person. So you would use meters, and the only way to get meters is to have things reprojected and transformed into this, what's known as universal transverse Mercator. Okay. Now again, there are actually thousands of other projections, but this is the most common one for used in the whole world, and in the most general sense. Like I said, used to cover the whole Earth, except for the Arctic regions, okay? In California, it's actually split kind of between Northern and Southern California, between Zone 10 and Zone 11 North, okay? ask yourself which zone is DVC, or which zone is Chabot, or which zone is somewhere else. Okay, these lines are fixed; they do not shift, or at least they shouldn't shift locally. Okay. Okay. Little one is trying to go down for a nap, so Mama's handling that. Um, I think that's all I have to say on UTMs. It's quite a deep topic. Like I said, just ask me in the discussion boards. I'll be happy to explain this more. Um, Now, in terms of these projections, which one are you going to use? Okay, if it's UTM or if it's something else, if it's spherical or is it going to be projected, right? You got to ask yourself these different things, like what is really the purpose? What's the extent? Is it a global extent, or is it like a hemisphere or a pole, or is it a state or a city? Okay, each one of these projections is going to have a little bit different of a purpose, depending on uh, what the size is, and then where's the location, okay, latitude wise, latitude longitude wise, and what's the objective, right? Because we have to take into account how much distortion is going to happen in these cases. Let's move on. Okay, a couple other terms I want you guys to know: transformation versus project. Okay, so project and projection, they are a little bit different. Transformation would be the first thing when we need to convert from one datum to another. Okay, so say we have a data set and it needs to be referenced to another origin. Technically, we could do that. That would be known as a transformation. Okay, these are actual technical terms, and there's tools in ArcMap. If you type in either one of these in the search bar, both of these will come up as various tools. So you could take the data you have, transform it to some other type of datum, or you can do what's called a project. Okay, not project, but project, and that would be to convert from one. That would be to convert from a geographic coordinate system like a latitude longitude to a projected coordinate system like a UTM. So if our shape files we put in came in and they were latitude longitude reference, then say we wanted to make measurements that were in meters, we could project, use the tool project, and then it will take our data and it will convert it to like a UTM zone. Okay. Um, let's see. Moving on. Just some little things to really take note of. And this is where things get really tricky, and why you guys have been getting warnings, and you will continue to, especially with lab 4 and 5. And it's okay, just as this introductory course, I'm not super worried about it, because like I said, ArcGIS will do what's called reproject on the fly, essentially put all your data kind of together so you can at least visualize it and move things around in what makes sense. But there is a difference between the data frame, or let's just put it this way: the data frame has a coordinate system, and the data sets also have their own coordinate systems. Okay, so the data frame. Okay, I don't know if are totally clear on that, but your data frame is, think of that kind of like the box where all of the layers are going into. That box has its own coordinate system. Could be world geodetic coordinates like lat to lat long, or they could be UTM or projected. Who knows? Just depends. The default that's going to come up if you just open up a blank map is going to be latitude longitude. Now the data sets you throw into the map, though, those will have some other type of defined coordinate system. Could be lat long, or they, if say you have 10 different data sets from 10 different sources, they could all have totally different coordinate systems altogether. Okay, so things will look right, but the reason why you're getting those warnings and asking if you want to do transformations is because all of the things we've just talked about. Okay. Okay, so important to understand. I'm putting exclamation points that you should always do a transformation. You know, try it, but I'm not saying, I'm not actually requiring it. Okay, because I know that your data is gonna pop up in what's known on-the-fly visualization. This right here, the ability to on-the-fly visualize and reproject, eliminates the need to transform data for many applications. And for everything we've been doing in this class, lab-wise, it's not really a big deal that we have to necessarily worry about. But you're welcome to try, okay? Let's see. Let's move on. Now, you could change the projection of the data frame. Here, I want us to all try this now. So, like I said, there's no actual lab I need you guys to turn in, but this is a good time to try this out. And so what we could do is go into ArcMap here. I'll put this kind of side by side like this. And I have ArcMap already pulled up. Okay. Where am I going to put my face? How about there? Move that and move this. So I've got a blank map here. Nothing to really do, or no data actually in the map itself. What I want to do, let's go ahead and try this. Okay, I'm going to add a base map first. Okay, and we know how to add a base map now after doing lab 4. So I'm going to go and say add, where the add data button is, and hit this little arrow and say add base map. And for the heck of it, I'm going to go ahead and do, let's try the National Geographic down here. Doesn't matter. You guys can do whatever one you want. Okay, so I'll go ahead and add that. And where to go? Oh. Zoom. There we go. Wow, my graphics are acting really odd. What's up with that? Huh. Okay, there we go. So here we are. We have regular old base map in there. Now, what I want to do is right-click on the up here where it says layers. This is that box that houses everything else. So technically, when you right-click on the layers text, you are changing or modifying or viewing the properties of the data frame. That's what's called the data frame. So if I right click on this, I can go to properties, okay? And like I said, this is your data frame properties. So select the tab coordinate system down right here, okay? And view the current selected coordinate system of your data frame, which is right here, okay, called the Web Mercator sphere. So actually, it didn't come in as a latitude longitude. It actually came in as, or it actually is showing a projected coordinate system. Now, the reason that, like I said, before we added the base map, it would have shown up latitude longitude. The first layer that we add into the software, in this case, the first layer is technically the base map. The data frame will take that, whatever that layer's coordinate system is, and make itself that same coordinate system. So if we only have one data set that we're working with, in this case a base map, or if it was with a shapefile, the entire data frame would take the properties of that particular coordinate system. And so for this base map, it's projected as what's known as a Web Mercator, which is very, very similar to a UTM. But I have all these other choices here, actually thousands and thousands and thousands of different choices. So let's try something different, okay? Select a different coordinate system and say okay. So let's try a few different choices. I honestly have no idea which one I'm going to pick. Maybe something like polyconical. Let's see what that does. Here, I'll move this over here. Apply. There we go, right? So this is polyconical. I guess that means there's actually two different cones looking at the world, right? So now the coordinate system of the base map has changed. If I change it to, let's say, okay, how about cube? Apply. You know, look how odd that looks. But for some reason, this is out there and this exists because it's, I imagine it's something related to the equator. Down here by the equator, you're going to get the most accurate and the most precise, representation of that part of the world. Maybe I want something like, let's go for a UTM. How about UTM, North America? Let's go with that zone. What were we talking about? Zone 11 in the slides. Let's see what that looks like. Aha. So the coordinate system has geographic coordinates that's different from one or more data sources. Essentially, this is telling me that now my datum is different. Okay. And I could push this transformations button and go through a little bit of a process to actually best practices make this thing as, remove any loose ends I might have so they don't get this pop up anymore. But I don't have to. I could just say yes. I could actually say, don't warn me about this again, but I can say yes. And it will actually reproject things in a visual sense to be where they're supposed to be. So let's go ahead and roll with that. And I'm getting the warning again. There we go. Now notice it's not really showing up well here on the screen. Let me show you there. You may not have noticed this before, but in ArcMap, down at the very bottom right of the screen, you have coordinate values. Okay, so anywhere that you move your mouse in the software, it's going to show you the coordinate of that particular location where your mouse is. So right now, like I was saying, UTM is in meters. And if I count those out from the X and the Y value, we have 6 digits for hundreds of thousands, for east and west or longitude, and then we're going to have 7 digits, something in the millions. In this case, 560,000 and 4 million in that case. But yeah, I mean, honestly, what I want you guys to do, take a little bit of time so that you have a better understanding of this, because you will be examined on this, is to kind of play around, right? Just play around with the base map, play around with some of the shape files or data sets that you have and see what happens, okay? Great. So just to summarize, all right, accurate depiction of the Earth's location depends on the shape of the Earth and whether that's a sphere, a ball, ellipsoid. If we're using geoid, that makes a difference, right? Location, and a projection system matters, but all projected coordinate systems are going to have some type of distortion or error, okay? And let's see. Just to keep things tight, nice and neat, the spatial reference of different data sets should be the same, although we know that something like ArcMap is going to reproject them into revisualize them in a way that it makes sense for us. So it's actually, in this case, introduction course, I'm not requiring it, right? But it is important to understand this because you might be called upon for specific reasons of having the extents, location, area, whatever it is, be utmost priority. And that's when you have to make sure you choose the right kind of projection. Or at least if someone, tells you what the projection is, that you understand how to go in and make that kind of modification, okay? And this is chapter 3, so definitely read chapter 3, and there's a couple other links here from the author that can help you out. Like I said, there's no lab, so that's it. Great, everybody. So I hope you took some good lessons away from that. I'm going to go ahead and wrap this up. But that is our lecture on coordinate systems. As mentioned, this is definitely going to be information that you need to know for your second exam, which wraps up the semester. Okay, thanks, everybody. Have a great day.